Hello, my name is Autumn McSwain, and this is my lab for Oscillations report. So, the purpose of this lab was to examine the motion of a spring mass system where the mass swings in an arc while simultaneously oscillating on a spring. This lab took place as a video that went into Tracker, where I manually tracked the observed position and then imported the data collected from Tracker into GlowScript to make a computational model of the data. The goal of this lab was to be able to determine if the model follows the energy principle. And, as shown later, the total change in energy was 0, which demonstrates the energy principle, and the predicted motion and observed motion between the x and y motions are very similar. So, some key concepts to know is Newton's second law, which states that the acceleration of a moving object depends upon the masses of the forces acting on it, which is F net will equal momentum divided by time. From this formula, we're able to derive the velocity update formula and the position update formula, where the velocity update formula is v final will equal v initial plus F net divided by mass times delta t, and the position update formula states that position final will equal position initial plus velocity average times delta t. From Newton's second law, we're also able to calculate the spring formula, which is the force of the spring and gravity that will create a net force, which gives us the spring formula, which is F net equals negative k absolute value of L minus L initial times L hat plus mg y hat. It's also important to understand that in this lab, the force of gravity is working down and the force of the spring is working upwards, and F net will equal the force of spring plus the force of gravity. Another key concept to understand is the energy principle. This is a fundamental principle that states that energy cannot be created or destroyed, but only transferred from one form to another. This is stated by the formula delta E system equals W surroundings plus Q, which states that the change in energy of a system equals the work done on the system by the surroundings plus the exchange of thermal energy between system and surroundings. And in this lab, the system was the mass, spring, and earth, and the surroundings was nothing. This is because, as stated previously, the force of the spring works upwards, whereas the force of gravity works downwards. This means that when we add them together, they're going to equal 0, so then F net will equal 0. This is why delta E of the system will equal 0, and delta K plus delta US plus delta UG will also equal 0. And some other useful formulas that will be important later is the kinetic energy formula, where K equals 1/2 mv squared, gravitational potential formula, where UG will equal mg delta H, and the spring potential formula, which is UG equals 1/2 ks squared. Which brings us to the lab. The first part of the lab is Tracker. In Tracker, I put a pre-made video that was given to me, which is shown on the left, which is a picture of it when it was in Tracker, and then in the center is my data from Tracker, with my x data on the top and my y data on the bottom. It's also important to understand the object's mass was 0.402 kilograms. The change spring length was 0.7 meters. The initial position was the vector negative 0.107, negative 0.6320 meters, and the initial velocity was 0 meters per second. The initial velocity was 0 because the object was initially being held when the tracker started, so it did not have any, it wasn't moving, it was still being held. From this data, we're able to solve for t, which is the oscillation period. To get the oscillation period, we're basically going from the trough of one to the next, or you can do it from the top as well. I did it from the top, so I did it from 1.52 seconds, 1.564 seconds, and 1.615 seconds, and I just divided that by 3 to get an average oscillation period of 1.56 seconds. And then k was given to be 6.83, and the relaxed length was given to be 0.123. Now, with all this data, I was able to build my computational model. So my initial conditions were imported, where the ball mass was 0.402, the ball position vector was negative 0.107, negative 0.632, and the ball velocity vector was 0. It's also important to make sure that you include the gravitational force, which is 9.8, the spring constant, which is 6.83, and the relaxed length of the spring, which is 0.123. With that done, we were able to move on to the springs and energy part. In this part, I had to give the length and orientation of the spring, which the length will be ball position minus the spring position, and L hat will be L divided by the magnitude of L, which gives us S will equal magnitude of L minus LO, which is basically the inside part of the parentheses of the spring formula. And then below are the formulas for the other important topics, such as the kinetic energy one, where K equals 1/2 ball mass times magnitude of ball velocity times to the second, and then gravitational potential energy, where UG equals ball mass times gravity times ball position y, and then spring potential energy, which is US equals 1/2 times KS times S to the second, and then the total energy will be E equals K plus UG plus US, as those are all the different forces that are acting in this experiment. So now we're able to do the prediction loop. So to begin with the prediction loop, you had to define initial energies, which are shown. I then had to calculate the gravitational force, which is basically just Fg will equal negative mg. So the force of gravity will equal the vector 0, negative ball mass times gravity 0, and this is only in the y coordinate because gravity works downwards only. Next, I had to calculate the force of the spring, which is Fs will equal negative ks L hat. So the force of the spring will equal negative k underscore s times L hat. Next, I had to calculate the net force. So F net will equal the force of springs plus force of gravity as stated before, where F net equals Fs plus Fg. Then I used Newton's second law of object's velocity and the position update formula to get ball velocity will equal ball velocity plus F net divided by ball mass times delta t, and ball position will equal ball position plus ball velocity times delta t. Next, I was able to update the spring, which will just be L equals ball position minus spring position, and L hat will equal L divided by mag L, and S is still mag L minus LO. But now we have spring axis will equal L, and the trail appendix will equal position equals ball position. And then the below are the energy changes. So with that done, my computation model came out to demonstrate what is shown on the left, where it created this like rectangle of ellipses, I guess, in a way. And when I put my tracker data and my computational model together, I got the graph in the middle. On the top is the x-axis, and on the bottom is the y-axis. And as you can see, in the x-axis mostly, as time goes on, the two models tend to deviate, which means that there is error or differences between the model and the experiment that occurred to cause them to deviate. While it may not look like much, if it continued to go on, it would slowly become farther and farther apart. The same thing is happening in the y position. It's just not as noticeable since they kind of overlap more. Now, reasons for this error could be not accounting for other forces, because in reality, other forces such as air resistance could affect the system, causing it to slow down faster, which is seen here by how the model is ahead of the experiment. Another reason for error could be tracker just not being accurate. Tracker is very glitchy, and the auto tracker function often fails, and manually clicking is just not always going to be the best because of human error. So there may be some tracker error. Another reason for error could be just not accounting for other energies, such as like rotational kinetic energy, because there are just other energies that could also be playing into this experiment. So that brings me to my what does this mean questions. Is the energy principle satisfied? As stated earlier, the energy principle was satisfied. This is shown in the change in energy versus time graph, where the change in kinetic energy, which is blue, the change in gravitational potential energy red, and the change in spring potential energy green all seem to cancel each other out. This is demonstrated by how the total change in energy is constantly 0, as shown by the total energy line, which is orange. It stays completely at 0 and does not move, which means that the total energy is 0. The spring potential energy is also in the opposite direction of the gravitational potential energy, which creates a sum of 0 for F net, which, if we recall from earlier, delta E of the system equals 0, and delta K plus delta US plus delta UG equals 0. Therefore, there are no external forces acting on the system. Therefore, the energy must be 0, as the surroundings is 0. So the energy principle is satisfied. Now it's time to estimate oscillation periods for the x and y axis. To do so, we first have to calculate the average oscillation period, which can be done by finding the average of 3 cycles, which is done below, where I took the total second and just divided by 3 because I had gone to the second where I was 3 troughs in, which gave me, for x, t would equal 1.646 seconds, and then for y, t equals 1.5197 seconds. This difference impacts the calculation of spring constants as shown by how k equals 5.858 for x, and the y-axis it's k equals 6.872, which shows two completely different oscillation periods, as x is 5.858 and y is 6.872. Now, why is it significant? The difference not only impacts the spring constants as demonstrated, but it also impacts the spring force and the spring potential energy. Now, some reasons for this difference could be drag or camber distortion or even tracker error, but those are the two estimated of the oscillation periods that I had. Thank you for watching my lab.